Good morning to everybody. I can see faces are already a little bit tired. I've got a bit of a cough, so if I start coughing, it's not part of the presentation. But this presentation is quite close to my heart. We're talking about AI networking. And at this point, I think talking about AI or mentioning AI is a cliche. Everybody wanna say something related to AI, right? Even if they previously called it something else, now they are rebranding it and calling it AI. But this is, I'm not gonna talk about any particular application, how you can, use ChatGPT or anything fancy like that. It remains a very pure networking discussion. This is basically my story of trying to understand what is AI doing coming into our world of networking. What is different about this AI application? It is another application. I already have routers and switches. I already have our protocols. What is different about it? What challenges it put to my network? And then what capabilities I have in my network to fulfill those requirements, meet those challenges. And I will talk about some of the enhancements that we did in SONiC to work with, to meet these AI networking requirements. I'll also touch upon why we think Ethernet is the right network for AI workloads. And if at the end we have time, I will also touch upon some of the work we are doing at Ultra Ethernet Consortium to make Ethernet scale for the networks of the future. So that is the agenda. Let's make a start. I often frame this discussion by contrasting AI networking with the standard cloud computing, because the first question that comes to mind is, if anybody's saying, let's talk about AI networking, you want to say, hang on a minute, right? What is AI networking? Networking is networking, right? Is it another gimmick? So let me give you a contrast in the very beginning. Think about cloud networking. I would say cloud networking was trying to solve a problem called virtualization. Would you agree with me? We're talking about, we have a server, we have some memory, we have resources. Let's virtualize it so we can run multiple applications on the same hardware, on the same resources. Now, if you compare it to AI, it is quite the reverse. Here we are talking about not one GPU or tens of GPUs. We're talking about hundreds of GPUs need to work together to support one application. It is quite the reverse, right? And what I just described, that multiple machines need to work together to support one application, actually I was just giving you a definition of distributed compute problem, right? So the first point I want to make here is that AI is basically a distributed compute problem. And in any distributed compute problem, networking becomes very important because all these multiple computers need to work together, need to act like a single computer. And they can only do it if they have a very efficient network. So the performance of your AI infrastructure, I would argue, depends on how efficient is your network. So that is why we say network is the computer. And this is not a Broadcom statement. This came from Sun about 20 years ago, but this is still very true. For a distributed compute problem, network is the computer. And the picture I'm showing here, this is basically, once again, quite an old picture. This is from a Google data center, where I would say Google was trying to solve previous generation distributed compute problem. And what was that? Search. And they did a good job, right? They did a good job. They solved that distributed compute problem with their technology. But what do we have here? I just said we solved the distributed compute problem. Here I'm showing you a slide from Meta, from Lexi, which she presented a couple of years back at OCP Global Summit. And essentially what she's saying here is, network is the bottleneck. We are the bad guys once again. Welcome back to the past, right? We used to be the bad guys, we are bad guys again. Why? The point she's making here, and it's a very valid point, is that these are different ML algorithms that they are running in their network. These are basically recommendation workloads. So these are the ones which make sure that, you know, yours and my children, they keep looking at Facebook and Instagram because they recommend the next thing and the next thing and the next thing, and they don't want to leave that, right? They are very intelligent algorithms. But the issue here is, what Meta is saying is that in some of these cases, 57% of the time is spent in the communicate phase, right? You know the compute, communicate, synchronize phase in machine learning algorithms, right? If you add all of these 4 different algorithms, if you add the time spent in networking, it averages out to be around 35%. That is 1/3 of the time our GPUs are waiting idle, waiting for networking to complete its job. Network is getting in the way of these AI infrastructure. Now, networking is only 10% of the cost of building an AI infrastructure. But if network is not done right, it costs a lot more, right? Let us try to understand why that is the case. We thought we had solved that problem. Why we are facing this problem with AI networking? It means there is something different fundamentally with the AI workloads. And I will make 3 points here very quickly. When you look at GPU to GPU communication, I'm talking about the back-end fabric, I'm talking about where GPUs are talking to other GPUs. When you look at that traffic, what you will notice is that there are relatively less number of flows, because less number of GPUs, and they are exchanging a lot of data. And when I say a lot of data, I'm talking about, you know, communication between 2 GPUs lasts for a very, very long time, sometimes weeks. Communication from one GPU to another GPU. Training job is ongoing for a week, multiple weeks. Communication is ongoing, right? Compare it to cloud computing. You have hundreds of flows, thousands of flows, and they are short-lived flows. Here we have small number of flows, and they are very long-lasting flows. What is the challenge it poses to networking? There is less entropy. Our standard network are based on ECMP. Right? We expect a lot of traffic is going to be there. There will be a lot of entropy, and we will be able to load balance. Not in this case. This is like, rather than going from your home to office, you take your car. In this case, you are taking a truck, 18-wheeler truck to office. And when you get onto the motorway, rather than using different lanes, everybody's just using one lane. But the point I'm trying to make is, if in this case, doing the load balancing is a challenge because of the low entropy. The second problem, we are talking about predominantly RDMA traffic. RDMA inherently has very poor retransmission algorithm. You know what type of algorithm we are talking about here? Go back to 0. Go back to n. What it means is, when you drop a packet, you're not essentially retransmitting a single packet. You are retransmitting a large number of packets. It depends where the checkpoint was made. So once again, packet drop is not a small problem. It's a big problem for us, right? It is like, as I was saying, giving you an example of that 18-wheeler truck. It's like you were on the motorway and something went wrong. Now you have to go all the way back to your home and then start your journey again, right? It's going to take a long time. And the third point, and probably the most important point, tail latency. These machine learning algorithms, they work with this compute, communicate, and synchronize phase. And they do this multiple iterations, right? They do compute, they're calculating some matrices, then they're communicating those, and then synchronize, and they start again. Then they start again, then they start again. But the next cycle, now this is the key point here, the next cycle does not start until everyone has finished their job. Have a look at this graph. What I'm trying to show here is this orange type GPU has completed its job here. This yellowish GPU completed its job a little further, but they do not start the next cycle until the last GPU has completed its job, this gray GPU. Once this last one has completed its job, everybody starts again. The point here is that a single slow flow will slow down everybody. And that is a killer for your job completion time. This is called tail latency, and that is a killer for your job team. That is why you see like 55% of the time is wasted in communicate phase, right? So now, let's double click on it again, and let's try to understand at a very low network level, what are the problems we are facing? Where are these delays, these issues coming from? And there are 3 points in the network that I will very quickly highlight. I started 11:35. Okay, so transient oversubscription, flow collisions or incast. Transient everybody understand oversubscription. Now, oversubscription is not a big contributing factor generally on the GPU backend, this backend fabric, because everybody makes non-oversubscribed networks. So I won't spend too much time on it. Flow collision is a genuine problem. Flow collision happen when two flows try to use the same link at the same time. And this will happen a lot. I just showed you the nature of the traffic. Everybody completing the job. Once the job completed, everybody starts again. There will be flow collisions, right? And that causes a big problem. Link failures. Let's face it, optics are still flaky, right? If you have your large enough network, you will have optics, they will fail. And we know that RDMA traffic is not very tolerant to packet drops. Problem will come. Incast. Multiple GPUs are trying to talk to one GPU, right? We talk about all-to-all, all reduced type communication. Multiple people are talking to one person. Of course, there will be congestion, right? It cannot take traffic from everyone. How do we solve this problem? I'll skip one or two here. I'll just mention one thing actually here. For this transient oversubscription, this is still a problem, especially when you use IP storage. Those IP storage type networks, sometimes they are still oversubscribed. We worked with Alibaba on this one a lot. There is a publicly available presentation on that, where Alibaba used one of the Broadcom technology, this in-band telemetry feature with HPCC++, which is a standard. So with HPCC++, what they did was they reduced tail latency in the network by half, by 50%, right? So this is a really cool technology. It's not something which lives on papers. It is actually being used by the customer, solving real life problems. I will give you a link at the end of the presentation where Alibaba went with Broadcom and talked about that. So that is very good way of fixing that transient oversubscription problem. Flow collisions. Remember the problem I talked about. There is low entropy. How do you solve that problem? You need to be able to utilize your available paths in a better way. There are two solutions that we suggest at Broadcom. Number one, packet spraying with receiver ordering. Easier said than done, right? If I say do packet spray, if you have received one flow, spray it across all the links. This is perfect load balancing. The challenge is on the receiver side. Now you have to reorder them, right? We have some technology which can work with that. I would focus more on the second one because we are here for the SONiC. Cognitive routing. This is our load-aware ECMP mechanism. This is the technique that we are using with SONiC, and a very good technique, and I'll touch upon that. Last point I mentioned was incast. Multiple people trying to talk to one person. We believe this problem is best solved at the receiving end. It could be the last hop leaf switch, or it could be the receiver itself. if you build that capability into it. The capability that we are suggesting is credit-based flow control. Receiver issues credit to the sender, how much traffic it can receive, right? There is some discussion ongoing about it at UEC, Ultra Ethernet Consortium. There are some other friends who want to propose a source-based credit control. I don't know which one will be finalized, but within Broadcom solution at this point, this is the technique that we are using, where is receiver-based flow control, credit-based flow control, which solve your in-cast problem in a very efficient way. And these are the two solutions we have at Broadcom. The one on the left-hand side is what we call switch schedule. This is based on Jericho 3 AI silicon. As the name suggests, this is switch scheduled fabric. All the networking related capabilities that you need, all the capabilities that you need to meet AI networking requirements, we have built them into this switch scheduled fabric. Now, it does not matter which NIC you use, it does not matter which GPU you use, it'll just work. Network will take care of it. I won't have time to talk about it in detail, but what you see on the right-hand side, this is what we call endpoint scheduled fabric. This is based on our Tomahawk 5 line of silicon. This is where we use SONiC to solve the AI networking problem. And in this case, as the name suggests, this is endpoint scheduled, which means that the endpoint need to play a part in the congestion management. And that is where your endpoints will run ECN and PFC and those type of standard-based protocol to participate in the congestion management. And there are some enhancements that we have made on this domain, both on the silicon as well as on the SONiC side. So on the silicon side, we have global load balancing. The idea of global load balancing is that we think about it, when you're using your standard ECMP type solution, we are only looking at the links attached to a switch, and we look at what is the best available path. With the GLB, global load balancing, we have a view of the whole of the topology. Think about it like your car's GPS system. When you're leaving your home for work, your GPS system will tell you there is congestion 3 roads down on the motorway, use the other path. We are bringing those capabilities into our network. How do we do that? We run an embedded app on the silicon, which can provide you this functionality. Reactive path rebalancing, once again, a very cool feature for AI applications. The idea is, remember I told you, communication between 2 GPUs can last for a very, very long time. What if you did a flow collision and for whatever reason, 2 elephant flows were pinned to the same link? If it was a cloud computing application, it's okay. After 15 minutes, it will sort itself out. If it is AI, you may be running on it for 2 weeks, right? So with reactive path rebalancing, we continue to monitor the best available path, and we will rehash your link to a different path if a better path becomes available. We have fast failover built into the silicon. You can failover. I'll show you actually some numbers, benchmarking numbers. We can do really fast hardware-based failover. That is, so we have no or least number of packet drops. And I'll leave DCN for now because I don't have enough time. Okay, from a SONiC side, we are very proud that we are one of the largest contributor to SONiC and SCI project, right? I was talking about VXLAN EVPN earlier. We are the ones who developed it, upstreamed it, and it's available in Community SONiC. When you run Community SONiC, close to 50% of it is Broadcom's contribution. And everything that we do create, 70, 80, 90% of that is upstreamed. Now, whether community accept it or not, or how long it takes, that's a different debate. But from Broadcom's point of view, we do not want to take people to an island. We are a strong believer in open source and contributions. What did we do on the AI side? Adaptive routing. The idea of adaptive routing is, rather than doing static ECMP, look at the qualitative metrics of a link, and then assign a load. What it means is that if there is, for example, I have 4 links on my leaf switch, and if I see that link 1 is heavily utilized, even if my hash is saying send the next link, next traffic to link 1, because it is heavily utilized, I won't use it. So you are looking at the quality of the link, you're looking at the congestion of the link, and then you're assigning it. And there are some other things we do there as well. So that's the adaptive routing, which helps to solve that load balancing problem for you. Advanced hashing. One of the problems with RDMA traffic with Rocky V2 is everybody looks same, right? Because everything is RDMA header is encapsulated, your QPR IDs are encapsulated. When you look at the 5 tuples, a lot of the traffic looks same. Where do you get the entropy if the traffic looks same? The answer is you have to look deep inside the packet. You need to look inside the RDMA header, look at the queue pairs, and then you can get entropy and you can do load balancing. That is the capability that we brought into SONiC. You can do that. This is called UDF hashing, user-defined field hashing that we do. The second thing we did on this regard is we added a new hashing algorithm called versatile hashing. This is on top of RTAG 7 hashing, and this gives much better results. It's been proven in our testing. It gives much better results for hashing your traffic. So we are, taking this load balancing problem head on with multiple techniques, and the results, I will show you some results. Results are very good for AI networking. Now, congestion-free operation, once again, it is all based on standards. It is all based on, the Rocky V2 that we all know, as other people have also deployed. What we did with SONiC is we made Rocky V2 deployment as simple as you can imagine. When you enable Rocky V2, you're doing 3 or 4 things. You're enabling ECN, you're enabling PFC, you are creating lossless buffers. You're doing all these buffer allocation on a per port basis. There is only one single command on SONiC to enable this, enable all of that on a full switch. You have 48 port switch, you say Rocky enable enter, and that's it. Off you go. It's enabled. All of this is enabled on all 48 ports. Made it very easy. Last thing, multi-tenancy, VXLAN EVPN. Once again, there are customers who are asking for multi-tenancy capabilities at the back-end fabric as well. Who are those? Some of them are who are offering GPU as a service, right? So they want to have multi-tenancy on the back-end as well. Traditionally, we did not support VXLAN EVPN in SONiC for Tomahawk line of family. But with Tomahawk 5, SONiC, we do include VXLAN EVPN support with SONiC as well for Tomahawk 5 for this particular use case. I think I'm almost at the end, yeah? 2 minutes. Okay, let's finish this off. Skip this slide. Because of its heritage in HPC, many people thought that InfiniBand will be a dominant technology, networking solution for AI. The reality is AI traffic is very different from HPC application. I can spend 15 minutes on it to talk about it. I don't have time today. The reality is multiple benchmarking tests have been done, and it shows that Ethernet beats InfiniBand every day of the week, twice on a Sunday. Right? Job completion time, we are at least 10% better than InfiniBand on all message types. And not just the performance, failover. That is a key point. Anybody who's deploying InfiniBand, please talk to them about this. Please ask them to compare InfiniBand with standard-based Ethernet technology on failover, and you will be surprised. We have done multiple benchmarking on this. We used, I've got 2 minutes. Okay, so 1600 microsecond for InfiniBand and 53 microsecond with Ethernet. We fail over 30 times faster than InfiniBand. You have a large enough network, you will see some failures. Ethernet won't let you down. And Ethernet is the de facto standard for AI. Don't take my words for it. 8 megascalers have deployed GPU-based AI infrastructure. Most of the GPUs deployed today, over 90% in my view, are at megascalers. 7 out of the 8 megascalers use Ethernet and not InfiniBand. There must be a reason for that. And I told you the reason. Ethernet is better. With Ultra Ethernet Consortium, what we are doing is we are modernizing RDMA. There are some inherent inefficiencies in RDMA, and we are fixing those. Call to action, final words, we believe AI networking requirements are different, but Ethernet and SONiC has the right feature set to meet those requirements. Do not go for proprietary features or proprietary vendors. Use open standards, use Ethernet. It won't let you down. There is this HPCC++ video that I was talking about where Alibaba used the technology to fix the problem. You can hear the story from them. And finally, if you want to learn how to configure SONiC, you can have a look at my YouTube channel, Love to Network, because I do love to network. Thank you very much.